Okay, video number 3 is on, and we are still talking about numbers. This will be our last video that just deals with numbers and manipulating numbers, and before we actually start talking about chemistry. But this has to do with the metric system, specifically metric prefixes, and a certain series of metric prefixes that I will expect you to know and will not be giving you any cheat sheets on an exam. And then what we call the SI units, which are the common units of measurement that we use in chemistry. And then finally, using what's called dimensional analysis, which your textbook will call the factor label method. I call it dimensional analysis as a way of solving problems and doing unit conversion. So let's just take a quick look at what's called the metric staircase. And so when we say base here, this is the whatever unit we're talking about. So if we're talking about liters, the base unit would be 1 liter. If we were talking about grams, the base unit would be 1 gram. If we were talking about meters, the base unit would be 1 meter. As you get larger, deca means 10, hecto means 100, kilo means 1,000. So if we were talking about a kilometer or a kilometer, that's 1,000 of the base thing, which in that case would be meters. Deci means 1/10, centi means 1/100th, milli means 1/1000th. How do you write that? How do you convert between one thing and another? Find the starting unit and the ending unit. So let's say how many meters is there in 1 centimeter? And so if I said that there's 1 centimeter, and I'm going to go to meters, I'm going to go 1, 2 to the left. And so I would move my decimal point 2 places to the left. So 1 centimeter is equal to 0.01 meters. Another way is to say if I'm going to the left and doing this in scientific notation, I'm becoming more negative. So 1 centimeter is 10 to the minus 2 meters. If I'm going to the right and doing this in scientific notation, then my exponent is becoming more positive. 1 meter is 10 to the 2 centimeters, 10 to the 3rd millimeters, etc. And we can extend this metric staircase out beyond kilo in the sort of larger direction or below milli in the smaller direction. There's not a name on every step. Now we're going to every 3 steps. So 1/1000th of a milli is a micro, 1/1000th of a micro is a nano. If we go to 1,000 kilos or 10 to the 6th base units, that's mega. 10 to the 9th base units is giga. Well, there's a lot here. Do you need to know it all? And the answer is no. This is what you do need to know from me. Anything else I would give you in a problem what the conversion factor is, but you need to know all these powers, every 3 powers of 10 from 10 to the 9th to 10 to the minus 9th. Giga is 10 to the 9th is giga, 10 to the 6th is mega. You need to know that it's capital G, capital M. 10 to the 3rd is kilo. 10 to the minus 3rd is milli, which is a lowercase m. 10 to the minus 6th is micro, which is the Greek letter mu. And then 10 to the minus 9th is nano, which is a lowercase n. In addition to that, because deci and centi will come up, particularly centi comes up a lot because we talk about centimeters in various contexts. You need to know that deci is 10 to the minus 1 and centi is 10 to the minus 2. So these 1, 2, 3, 4, 5, 6, 7, 8 prefixes, their abbreviations, and their meanings you should have memorized by the time the class starts. There's also one more unit that we'll talk about, although it'll come in quite a bit later in the class, and that's what's called the Angstrom. And an angstrom specifically is 10 to the minus 10th meters. Again, that'll come into play later. You really just want to focus initially on these 8 that I have in the red box here. Okay, here's a pop quiz for you. What is the symbol and meaning that is multiplier for each of the following? You can pause the video if you want and think about it and then start again. So milli means 10 to the minus third, and its symbol is a lowercase m. Mega is 10 to the sixth. Its symbol is an uppercase m. Micro is 10 to the minus sixth. Its symbol is the Greek mu. The SI units, which are very similar in many respects to the metric units, but this is what's been adopted officially by the international scientific community as what were called the base units of science. And there are 7. And so the base unit for length is the meter. In the metric system, the base unit for mass is the gram, but in the SI system, it's the kilogram. And that has to do with the fact that certain other units like the Newton and the joule and things like that are based on kilograms, not grams. And so the SI unit of mass is the kilogram. The SI unit of time is a second. Volume is a liter. Temperature is the Kelvin. And then the mole represents the amount of substance. There's 1 or 2 other SI units that we simply don't encounter in our course, and so I haven't listed them here. So again, what are the standard prefixes that you need to know? I've got them bolded here. So 10 to the 9th is a giga, capital G. 10 to the 6th is mega, capital M. 10 to the 3rd is kilo, lowercase k. For measures that are smaller than the base unit, you need to know deci, 10 to the minus 1, centi, 10 to the minus 2, milli, micro, 10 to the minus 6, nano. So the things that are bolded, these 3 things that are bolded here, and these 5 things that are bolded here, same 8 things that I had shown you on that previous table that you need to have memorized. Okay, let's get on with the use of all of this, or at least the situation in which we would use these things, which has to do with unit conversions. And so what I'm going to teach you and what I will practice in class is called dimensional analysis, which again, some textbooks will refer to as the factor label method. But it's based on the idea that any equality between units can be turned into 2 conversion factors. And so what do I mean by that? Well, if I say that 1 foot is equal to 12 inches, then I can divide both sides of that by 12 inches. I'm sorry, I got it backwards. My first example is going to be I can divide both sides of that by 1 foot. And that tells me that so when I divide both sides of these by 1 foot, I get 1 foot divided by 1 foot, which is equal to 1, is equal to 12 inches divided by 1 foot. So there's a conversion factor here. 12 inches over 1 foot is equal to 1. If I divide both sides by 12 inches, I get another conversion factor, which is just the reciprocal of this one. But since they both equal 1, the reciprocal of 1 is 1. I can use either one of these as a conversion factor. And the question is, well, do I want to use this one or do I want to use this one? Depends on which units I'm trying to cancel out and which units I'm trying to keep. And we'll talk about that in just a second. Okay, now I will use consistently in class what I call the train track method, in which I will set up a horizontal line with a bunch of vertical hash marks like this to try and come up with an answer to a unit conversion question. You don't have to use the train tracks. You can use the method you want, but what I want to make clear what the train tracks mean. And what the train tracks mean is the same thing. Every time you see a crosshatch here, it's like a multiplication sign, okay? And so this little train track bit that I have set up here is the same as this. And so let's fill this in with some numbers. Suppose you were given the question, how many seconds are there in 1 year? And so I would set it up on the train tracks like this. I'm using a series of conversion factors and I'm setting them up so that they cancel each other out. Number of days in a year so that years cancel out, number of hours in a day so that days cancel out, number of minutes in an hour so that hours cancel out, number of seconds in a minute so that minutes cancel out. It means the same thing as this. And although I don't give the answer to this problem here, it's about 32 million seconds in 1 year. Okay, so let's try an example of that. And I'm asking you to calculate the number of meters in exactly 1 mile. And so what I want to do is convert miles into meters. And so I'm going to start with the measurement that I've been given, which in this case is actually not a measurement, but a definition, exactly 1 mile. And I'm going to insert conversion factors so that the miles cancel out and I wind up with meters. Now, you may already know exactly how many meters there are in a mile, but let's use some conversion factors that are more common that we actually do know. And before I put the numbers in, I'm just going to put the units in. So I know how many feet there are in a mile. That is a defined number. And so I'm going to set that up so that I've got feet on the top and miles on the bottom so that they cancel out. I know how many inches there are in a foot. That's an easy one. And again, I'm going to set the units up so that feet cancel out and I'm left with inches. On a previous presentation, I had mentioned to you that there is a definition that the centimeter and the inch are defined in terms of each other, or the inch is defined in terms of the centimeter. And so I can convert inches into centimeters in this fashion. And then finally, using metric prefixes, I can convert centimeters into meters. The reason I'm putting these in here without the numbers first is a lot of times people will rush to set these up and they will then wonder, well, I know that there's this many miles in a foot or there's this many, et cetera, et cetera. Am I going to multiply by that or am I going to divide by that? And by putting the units in first, that drives where you put the numbers in. So you don't really have to ask yourself. You just put the units in and then the numbers follow. So there are 5,280 feet in a mile. There are 12 inches in a foot. There are 2.54 centimeters in an inch. That's a defined number. And then there, from the metric system prefixes, we know there are 10 to the minus 2 meters in 1 centimeter. And when I multiply all that out, I get 1609.344 meters. Mr. Jones, there are 7 significant figures in that number. Why are you reporting that answer to 7 significant figures? The reason is because every single thing here is an exact number. You'll recall we talked about the difference between exact and inexact number. Well, I said we're starting with exactly 1 mile, so I'm defining that in the problem as being exact. Because this is a definition, feet per mile, these are exact numbers with infinite sig figs. Because inches in a foot is a definition, this has infinite significant figures. Because this is an exact number, that the inch is actually defined in terms of a centimeter, these are exact numbers, and metric conversions are exact numbers. And so every single number here is exact, and therefore every single digit that I get in my answer is significant and meaningful. There are exactly 1,609.344 meters in 1 mile. Okay, now let's try another one. Convert 60 miles per hour into meters per second. Okay, so I am given 60 miles per hour. Now I'm wanting to do a couple things. I'm wanting to convert miles into meters, and I'm wanting to convert hours into seconds. So miles into meters in the numerator, hours into seconds in the denominator. So I'm going to, first again, I'm going to set up the units before I put in the numbers. I'm setting up meters on the top because I want to keep meters in my numerator, miles on the bottom so that they'll cancel out. Converting hours to minutes, canceling out hours in the denominator by putting it in the numerator and bringing minutes into the denominator, and then canceling minutes out of the denominator and replacing it with seconds by arranging that conversion factor in this way. Once I've arranged the units, the numbers go in all by themselves. I mean, they just kind of follow. So we just on the previous problem figured out that they're 1,609 meters per mile. Because our measurement only has 2 sig figs, and I forgot to put a decimal point there, but because our measurement only has 2 sig figs, The fact that our conversion factor has 4 sig figs here is plenty. 60 minutes in an hour, but it's in the denominator because I'm trying to cancel out hours. 60 seconds in a minute, but it's in the denominator because I'm trying to cancel out minutes and put seconds into the denominator. When I put that all into my calculator, I get this answer, which actually goes on to infinity. I could just keep putting 6, 6, 6, 6, 6, 6, 6s. But let's figure out how many sig figs we're supposed to report that to. This is a measurement that has 2 significant figures, 60. This is a rounded number, but it has 4 sig figs. These are exact numbers. These are exact numbers. Therefore, the smallest number of significant figures in here is the 2 for the 60. And therefore, I'm going to report that as 27 meters per second. All right, let's do some examples. You can look at these and turn the video off and do the calculation, and then come back and turn the video back on and look at the answer. So how many seconds are there in exactly 3 hours? Well, my measurement is 3 hours, although again, I'm defining it as exactly 3 hours, so it actually has infinite significant figures. I'm going to convert hours into minutes by putting hours on the bottom and putting minutes on the top. I'm going to convert minutes into seconds by putting minutes on the bottom and seconds on the top. There are 60 minutes in an hour. There are 60 seconds in a minute. Because all of these numbers are exact, because I define this number as being exact, these by definition are exact, there are exactly 10,800 seconds in 3 hours. All right, let's try another one. Convert 550 nanometers to meters. Okay, I am starting with 550 nanometers, which again, I put the decimal point in there. I left it out here. We'll get back to that in just a second. I'm converting nanometers to meters. I know from my metric prefixes that 1 nanometer is equal to 10 to the minus 9th meters. I'm putting nanometers in the denominator to eliminate it and put meters in the numerator. 550 times 10 to the minus 9th is 5.50 times 10 to the minus 7th. Because my original measurement had 3 significant figures, even though I left out the decimal point here, my answer is going to have 3 significant figures, 5.50 times 10 to the minus 7. Okay, example 3. This, in my mind, I just put this in here to demonstrate to you what I think the power of dimensional analysis is, because here's a problem that you would probably look at, because we haven't talked about any chemistry yet in any of these videos, and say, how in the heck am I supposed to solve this? The concentration of a particular solution of sodium hydroxide, NaOH, you don't need to know that that's called sodium hydroxide, we just call it NaOH, is 0.250 moles per liter. MOL is simply a shortening of MOLE for mole. The molar mass of NaOH is 40.0 grams per mole. What mass of sodium hydroxide is contained in 35.0 milliliters of solution? But we haven't talked about any chemistry at all. How are you supposed to solve that? Well, just take a second, turn the video off, play around with some of the information that's given to you in this problem, and see if you can't use dimensional analysis to answer the question on your own. And if not, you can see my solution on the other side. Well, here are some things that the problem tells us. It tells us in here that 1 liter of solution contains 0.250 moles of sodium of NaOH. Right? The concentration of a particular solution is 0.250 moles per liter. So that gives me this equality, 1 liter of the solution. So that's a conversion factor or an equality that's given to me in the question. Another equality that's given to me in the question is what's called the molar mass, that 1 mole of NaOH contains 40.0 grams of NaOH. That's what I had written here, 40.0 grams per mole. And then we know from the metric system, one more thing that'll be helpful to us, which is that 1 milliliter is equal to 10 to the minus 3 liters. So can I take my original measurement, which is 35 milliliters of solution, and line all these things up as conversion factors in order to give me grams of NaOH? Well, I actually can, and I've done it right here. So I'm starting with my measurement, 35.0 milliliters. I'm using this equality and putting it in as a conversion factor so that milliliters are canceled out and giving me liters. Now I'm using this top equality and putting it in as a conversion factor so that liters are canceled out and giving me moles of NaOH. And then I'm using this middle conversion equality and putting it as a conversion factor so that moles of NaOH are canceled out to give me grams. You can see milliliters canceled out by milliliters, liters canceled by liters, moles of NaOH canceled by moles of NaOH. I have succeeded in converting milliliters into grams of NaOH, and the answer is 0.350 grams. So those are examples of dimensional analysis. This is a very powerful method. It is also something that you will want to become thoroughly acquainted with, so I strongly encourage you to do the worksheet to the maximum extent possible, and we will see you in the next video. Thanks.